Welcome to our quantum deep dive.
Great to be diving in.
Today, we're tackling Weyl Fermions, these sort of revolutionary particles, right? Based on that really insightful essay by Yorgo Schneeppert.
That's the one. Schneeppert does a great job laying it out.
And for you, the learner, listening in, we know you want to get complex stuff quickly. So our mission today, unpack what these things are, why they matter.
And yeah, their potential. It's huge. We'll pull the key bits from Schneeppert's work, but, keep it clear.
Exactly. Think of it as your fast track, your shortcut to understanding this really cutting-edge quantum physics stuff, hopefully with some aha moments along the way.
Let's aim for that.
So starting right at the basics, according to Schneeppert, what are Weyl Fermions?
Okay, so Schneeppert describes them as massless quasiparticles. Now, quasiparticles is key here.
Right, not fundamental particles like an electron floating in space.
Exactly. They're more like emergent phenomena. Inside certain materials, the electrons are forced by the material's structure to behave as if they are these theoretical massless Weyl fermions.
So the material itself creates the conditions for this behavior.
Yeah.
And massless is the big thing.
It's huge. Their behavior is pinned down by the Weyl equation, which is specifically for massless particles. And they have this property called chirality.
Chirality.
Like handedness.
Precisely. Think left hand, right hand, mirror images, but fundamentally distinct. Weyl fermions come in these left and right-handed versions. It's related to their spin and direction of motion.
Okay, so massless, chiral. How does that stack up against, say, an electron? Schneeppert mentions Dirac fermions.
Right, electrons are Dirac fermions. And the big difference, as Schneeppert points out, is mass. Dirac fermions have mass. Weyl fermions, at least these quasiparticle versions, effectively don't.
And no mass means?
It leads to this really specific energy-momentum relationship. E equals CVFK. It looks linear.
Linear, meaning?
Meaning they can move extremely fast, almost like light within the material, and with incredibly high mobility. Think near-resistance-free movement. That's a key takeaway Schneeppert highlights for electronics. Near-resistance-free. Wow, okay, but this idea isn't new, is it? Schneeppert takes us back to Hermann Weyl in 1929.
Yeah, the history is fascinating. Weyl was looking at Dirac's equation and wondered, what if the mass was zero?
Just mathematically.
Pretty much. He derived the Weyl equation from Dirac's equation by setting mass to zero, and his first thought, Schneeppert notes, was maybe these were fundamental particles.
Like, could they be neutrinos or something?
That was the hope! Neutrinos were mysterious back then, but then we found out neutrinos do have a tiny mass.
Okay. So the fundamental particle idea didn't quite pan out in particle physics.
Not in the way Weyl first envisioned, but the math, the Weyl equation itself, was sound. And it found this incredible new life, as Schneeppert explains, in condensed matter physics.
And these materials called Weyl semimetals, or Weyl halbmetal, as Schneeppert puts it.
Exactly. These are real materials where the electrons, because of the crystal structure and electron interactions, collectively behave like those massless Weyl fermions Weyl predicted.
So it's an emergent property of the electron soup inside the material.
That's a good way to put it. And Schneeppert details some really exceptional electronic properties that come out of this.
Like the high mobility we mentioned.
Definitely that. Extremely high charge carrier mobility. But also, Schneeppert stresses their robustness.
Robustness, meaning they're tough.
Sort of. It's because of topology. The points in the material's electronic structure where this Weyl behavior happens, the Weyl points have a topological protection, like a knot that's hard to untangle. They resist being destroyed by small imperfections or disturbances.
Topology. That sounds important.
Thanks.
Gives them inherent stability.
You got it. And then there's something called the chiral anomaly. Schneeppert flags this as really significant.
Okay, chiral anomaly. What's the core idea there?
Well, it's a purely quantum mechanical effect. If you apply electric and magnetic fields parallel to each other in these materials, you get this weird effect where charge seems to get pumped between the populations of left-handed and right-handed Weyl points. It looks like charge isn't conserved locally for one type of chirality, although overall charge is conserved.
Whoa, so you can move charge between these handed states using magnetic fields.
Essentially, yes. And the key insight Schneeppert offers is the potential for really energy-efficient electronics, maybe even logic gates controlled by magnetic fields.
High speed, robust, energy efficient. Sounds like a hat trick. Schneeppert mentions applications like spintronics, topological quantum computers.
Absolutely. The high mobility points to faster transistors. The chirality and spin connection is perfect for spintronics using electron spin for information.
And the topological robustness. for quantum computers.
That's a huge area of interest. Topological quantum computers promise to be much more resistant to errors, which is the big challenge right now. These Weyl systems, especially when combined with superconductors, might offer a pathway there.
Okay, let's dig into the theory a bit more. Schneeppert reminds us fermions have half-integer spin, obey the Pauli exclusion principle.
Right, standard quantum mechanics. And they're described by these relativistic equations, Dirac for massive ones, Weyl for massless.
And the Weyl equation splits into two.
Yeah, because there's no mass term linking them, it naturally separates into independent equations for the left-handed and right-handed Cura components.
And Schneeppert makes a distinction between helicity and chirality.
He does. Helicity is just spin direction relative to motion. Chirality is a more fundamental quantum property here. For massless particles like ideal Weyl fermions, they become the same thing. But chirality is the deeper concept linked to the Weyl equation structure.
Got it. And then topology comes back in with these Weyl points. Schneeppert calls them singularities.
Singularities are touching points in the energy momentum graph of the electrons. They act like sources or sinks of something called Berry curvature, and they carry a topological charge, like a magnetic monopole in momentum space. This charge is the turn number he mentions.
And that charge makes them stable.
Pretty much. You can't easily get rid of them without bringing 2 points of opposite charge together to annihilate.
Schneeppert says you need to break certain symmetries to even get these Weyl points to appear.
That's crucial. You need to break either inversion symmetry, the symmetry of reflecting everything through a central point, or time reversal symmetry, the symmetry of running the physics backward in time.
Why?
If you have both symmetries, the energy bands are forced to behave in a way that prevents these isolated Weyl points from forming. Break one, and they can pop up, usually in pairs.
And breaking these symmetries leads to different arrangements.
Yeah, break inversion, you get pairs with opposite chirality. Break time reversal, often using magnetism, and it gets a bit more complex, but you still get these points.
And he mentions Fermi arcs on the surface.
Yes, another consequence of the topology. These are unique electronic states that only exist on the surface of the material. They form open arcs that connect the points where the bulk Weyl points project onto the surface. Really strange behavior, leading to unique ways electricity can flow on the surface.
Okay, theory's fascinating. But Schneeppert highlights the big breakthrough came in 2015 with experiments.
Absolutely pivotal moment. Several groups, pretty much simultaneously, found the first experimental proof in actual materials. Not fundamental particles, but these Weyl quasiparticles.
Using what technique? Schneeppert mentions IRPs.
Angle-resolved photoemission spectroscopy. It's a powerful tool that basically lets you map out where electrons can exist at different energies and momenta in a material.
And they saw.
They directly saw the smoking guns, the linear dispersion, that E proportional to K relationship near the Weyl points, and they could even map out the Fermi arcs on the surface. Tantalum arsenide, TAs, was one of the first big ones.
So they literally visualized the signature of massless behavior.
Incredible confirmation of the theory, yeah. As Schneeppert notes, these materials don't have a normal energy gap. Like semiconductors, they have these specific points where the energy bands touch the Weyl points.
And besides ARPs, Schneeppert brings up electrical transport measurements.
Right, measuring how electricity flows. The chiral anomaly we talked about has a very specific signature, negative magnetoresistance.
Negative. So resistance goes down when you apply a magnetic field. That's weird.
It is. Normally, magnetic fields make it harder for electrons to flow, increasing resistance. But here, if the magnetic field is parallel to the electric current, the chiral anomaly pumps charge more efficiently along that direction, reducing resistance. Seeing that was another key piece of evidence.
Okay, so let's recap the key properties Schneeppert emphasizes. Massless dispersion.
Leading to that super high mobility, great for speed.
Chiral anomaly.
Giving potential for new kinds of magnetoelectronics, maybe super efficient ones.
And topological protection.
Providing that robustness, that stability against imperfections, which is good for reliability and maybe quantum information.
And Schneeppert really connects these properties directly to potential quantum tech.
For sure. Faster electronics is almost a given if we can engineer these materials well. The spintronics angle, using the chirality to filter spins, is very promising.
And the quantum computing link. You mentioned Majorana fermions.
Yeah, that's a bit more advanced, but the idea is if you combine Weyl semimetals with superconductors, the boundaries might host Majorana modes. These are even weirder quasiparticles that could potentially be used as qubits, the building blocks of quantum computers that are topologically protected against errors.
Wow. So Weyl systems could be a platform for fault-tolerant quantum computing.
It's one of the big hopes, yes. It's still early days, lots of challenges, but the physics outlined by Schneeppat is compelling.
So dissipationless currents, spin filtering, ultra-fast signals. The potential seems enormous.
It really does. The possibility of moving charge and spin around with minimal energy loss controlled in new ways, it opens up a lot of doors.
But Schneeppat also finishes by looking ahead, right? Open questions, future research.
Absolutely. It's a fast-moving field. A big one is just finding more and better Weyl materials. We need ones that are easier to work with, maybe with the Weyl points further apart in energy, more stable surface states.
Material science challenges.
Definitely. And also learning how to control and manipulate these Weyl quasiparticles precisely using, say, electric fields, magnetic fields, maybe light.
And he mentions combining them with other materials, like superconductors or magnets.
Exactly. Creating hybrid structures to unlock new physics or functionalities. Weyl superconductors, Weyl magnets, these are frontiers.
Schneeppat even touches on deeper connections, analogies to gravity or cosmology.
Yeah, that's where it gets really mind-bending. The mathematics describing Weyl points and anomalies turns out to have parallels in theories of gravity involving torsion, and even in models related to dark matter or the early universe. It suggests these concepts might be more fundamental than just condensed matter physics.
So studying these materials might even tell us something about fundamental physics.
It's possible, and of course, the ultimate question Schneeppat leaves us with, could there still be fundamental Weyl Fermions out there, perhaps beyond the standard model of particle physics? The search continues in high-energy experiments, too.
Okay, so wrapping this up, what's the big picture for you, the learner, from this deep dive into Schneeppat's essay? These Weyl Fermionen started as a purely theoretical idea from Hermann Weyl.
A mathematical possibility for massless particles.
And now, as Schneeppat details, they become real, quasi-particle realities inside certain materials with properties that could genuinely transform technology.
From the promise of faster, greener electronics because of that high mobility and chiral anomaly,
to maybe forming the basis of robust, fault-tolerant quantum computers thanks to their topological nature. The feature Schneeppat outlines, massless, chiral, topologically protected, are a potent mix.
Definitely. And while getting from the lab discovery that Schneeppat chronicles to actual everyday tech takes time.
The physics itself is already giving us profound insights, maybe even, as Schneeppat hints, into the universe's fundamental rules.
So this deep dive, guided by Yuri Schneeppat's work, just scratches the surface. What part of this quantum weirdness stood out most to you? What are you still curious about?
Thank you for joining our quantum deep dive into the really fascinating world of Weyl Fermionen. We absolutely encourage you to keep exploring. It's a field that's definitely going places.